There's a region of our planet that no human being has ever visited. No one has ever seen this place. Yet what happens here affects every one of us, every day of our lives. It's 2,000 miles beneath our feet. The Earth's molten core. Here, a vast ocean of liquid iron generates an invisible force. The Earth's magnetic field. It's what makes our compasses point north, but it does a lot more. It helps to keep the Earth a living planet. Our neighbors, Venus and Mars, have only weak magnetic fields, which means they're unprotected from the deadly radiation sweeping through the solar system. The Earth, on the other hand, exists within a vast magnetic cocoon. A force field that for billions of years has sheltered us on our journey through space. But now, scientists have made a startling discovery. It seems there's a storm brewing deep within the Earth. A storm that is weakening our vital magnetic shield.
It's the buzz when I'm full of your sweet magnetic pull.
The Earth's magnetic field has been our protector for millennia, and now it appears it's about to go away.
It's how
The Earth's magnetic field is getting weaker rapidly.
We cannot guarantee that the magnetic field of the Earth is still going to be there 1,000 years from today.
Is our invisible shield about to disappear?
The question is not if that's going to happen, it's when that's going to happen.
Could the Earth really lose its magnetic field? And what will happen if it does? Up next on Nova, Magnetic Storm.
Major funding for NOVA is provided by the Park Foundation, dedicated to education and quality television.
We see 400 employees in 3 years. At Microsoft, your potential inspires us to create software that helps you reach it. Your potential, our passion.
Science. It's given us the framework to help make wireless communications clear. Sprint is proud to support NOVA.
And by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you.
Searing heat. Crushing pressure. And a billion trillion tons of molten iron. These are the conditions at the center of the Earth.
This is the Sparrows Point blast furnace for Bethlehem Steel Corporation, and this is as close to the environment of the Earth's core as we have here on the surface of the Earth.
Buried beneath nearly 2,000 miles of solid rock, the Earth's core is inaccessible to geophysicists like Peter Olson.
About halfway to the center of the Earth, we reach the true heart of the Earth's core. An immense, molten sphere of liquid iron. And that's where the Earth's magnetic field is generated.
But recently, scientists have detected a dramatic change in the Earth's magnetic field. The core's ability to generate the field seems to be faltering.
Today, the something very strange is going on with the Earth's magnetic field. Its strength is rapidly decreasing, so fast that at the current rate, it will last only into the next millennium.
It seems the Earth's magnetic field is rapidly fading, a puzzle that is challenging scientists around the globe.
It's quite surprising how little is understood about the Earth's magnetic field and how it's generated.
It was a very intriguing problem, something that was screaming out for an answer. I often wished I could see the magnetic field. I'm motivated by the mysteries that are there.
As scientists grapple with the complexities of the magnetic field, they realize that what is happening at the center of the Earth could change our world for generations to come. Magnetism is something we're all familiar with.
Oh, look. At the end of the magnet, the paper clips stick to it. I can connect it. Oh.
Its seemingly magical ability to attract
I got 5 of them on.
and repel delights and baffles.
When the magnets are turned over one way, they don't want to go together. And when you flip them over, they want to come together and they stay together.
But this mysterious force is not just a curiosity.
Look at the TV.
Magnetism, a close relative of electricity, lies at the heart of most modern technology. Everything from power stations to the television you're watching now. And in fact, the Earth itself is a gigantic magnet. While we are constantly aware of the pull of gravity, most of the time we are oblivious to the other force the Earth generates, the magnetic field. But space scientists like Andrew Coates know how important it really is.
Magnetic field extent is really huge. It's the biggest thing really we have on Earth.
The magnetic field is created deep in the Earth's core. It streams out near the South Pole, loops around the planet, and then runs back into the core near the North Magnetic Pole. This is the Earth's protective force field. Without it, we'd be in trouble.
It protects us against radiation from space. It's a little bit like being in the pod here. This shields us from the weather on Earth. The magnetic field of the Earth shields us from space weather and space radiation.
Space weather is nasty. The winds that blow through the galaxy are winds of radiation. Some of the most harmful from distant exploding stars.
But there is another source which is much nearer, which is our sun. The sun itself is a thermonuclear furnace, and this flings off huge amounts of dangerous material in very large explosions. In some cases, it's about the same mass as Mount Everest actually coming towards us.
Every few hours, the sun ejects billions of tons of electrically charged particles, the solar wind. Often, the Earth lies directly in the path of this onslaught. But magnetism deflects charged particles. This means that the solar wind is unable to penetrate the Earth's magnetic shield, and so flows harmlessly around the planet. The only visible signs of this drama far above our heads are the northern and southern lights, produced when solar particles trapped in the Earth's magnetic field are dragged through the atmosphere toward the poles.
Now, we're lucky on the Earth we have the magnetic field which deflects the particles and protects us. But if we lost the magnetic field, there would be nothing to stop the radiation bathing the whole of the atmosphere, and the effect would be much more dangerous.
But just how dangerous? What would be the ultimate consequences for planet Earth if the magnetic field were to disappear altogether?
5, 4, 3, 2, 1. We have ignition.
The answer has become clear only recently.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the Red Planet.
In 1996, NASA sent a satellite to Mars.
Mars has been a difficult planet to get to with spacecraft. Even after 16 missions by US and Russia and so on, we still did not know whether Mars had an intrinsic magnetic field or not.
The Martian rocks.
It was this long-standing question which Mario Acuna and his team from NASA hoped finally to settle. What they actually uncovered was considerably more significant.
Nature had big surprises for us, beyond our wildest expectations.
Hidden in the history of Mars lay the connection between magnetism and life.
And here is where we develop our expensive toys, our instruments. This is our lab.
Mario is one of the world's leading experts on extraterrestrial magnetic fields. He has sent instruments to measure them all over the solar system.
This one went to Jupiter, Saturn, and beyond. This is Voyager 1 and 2. This one went to Mercury with Mariner 10. This one went around the orbit in the Sun. This one went to Comet Halley, for example.
To measure magnetic fields, Mario uses a technique which was discovered a century and a half ago.
The simplest way to measure a magnetic field is with a little magnet like we have here that has been mounted in such a way that it can move freely in 3 dimensions. And this magnet, because magnetic field is a force field, will align itself with the Earth magnetic field, in this case, in this direction that we have here, which is actually going into the core at an angle of 70 degrees here and pointing north. So that gives us an idea of the direction of the field. And you can see that, and if I perturb this magnet just slightly, how fast it recovers the original position gives us indication of the strength of the magnetic field. So it's very weak for the Earth, and if I use a strong permanent magnet, then we see that our test magnet moves much faster. So if I make this magnet work against a spring, I get an idea of not only the direction of the field, but also how strong it is.
In the Mars Global Surveyor satellite, the instruments are electronic rather than mechanical, but the principle remains the same. A tiny electromagnet which works against a magnetic spring.
So here's my spring, here's my magnet, and if I pass an electrical current through my spring and measure the disturbance of my magnet, which is inside, then I can transmit back to Earth the information about the strength and the direction of the field we are trying to measure.
As Mars Global Surveyor started to send back data, it soon became clear to Mario and the team that today Mars has no overall magnetic field. But the satellite also detected signs indicating that that had not always been the case.
We found these huge magnetic fields in the crust, and all of a sudden a completely unexpected and unknown planet, in a sense, emerged.
Although there was no magnetism coming from the core of Mars, strangely, large areas of the surface were strongly magnetic. The Martian crust is mainly made of frozen lava, a remnant of the time when Mars was covered with volcanoes. And there is a way volcanic rocks can get magnetized when they form. If molten rock cools in a strong magnetic field, iron-based minerals in it can pick up that magnetism, and the resulting solid rock will itself be magnetic. So, the fact that there was magnetism in the Martian crust proved that when the lava first erupted, Mars must have had a global magnetic field.
And And not only that, at an intensity which is 20 to 30 times that of the Earth.
And so that's basically similar to
Mario's team now knew that Mars had once had a magnetic shield, which it must at some point have lost.
Well, not most of them, but 30 or 40.
They began to wonder whether this might be the solution to one of the great mysteries of the solar system. Scientists suspect that the young Mars was in many ways an Earth-like place, with a thick atmosphere and oceans which may have harbored primitive life. But then, around 4 billion years ago, the planet entered a catastrophic decline. Gradually, the atmosphere and oceans of Mars mysteriously disappeared.
The puzzle was, where did the water go? What process could have caused the loss of water?
Mario realized that 2 dramatic events in the early history of Mars might lead him to the answer.
We found 2 very large impact basins in the southern hemisphere of Mars, which are Hellas and Argyre. There was absolutely no magnetization over them.
In these basins, formed when 2 huge meteorites hit Mars, the rocks were strikingly free of magnetism. And that was odd, because the huge impacts must have melted the crust. And as it cooled again, the rock should have become magnetized by the strong Martian magnetic field. Yet, there was no trace of magnetism in Hellas and Argyre.
Which immediately meant that they were formed after the magnetic field of Mars has ceased to exist. And the estimate is that these impacts took place more than 4 billion years ago.
4 billion years ago is when Mars was beginning to lose its water and atmosphere. Though not all scientists agree with him, Mario is convinced that the timing is not just a coincidence.
If we shut down the magnetic field, then the solar wind has direct access to the atmosphere of Mars. Then we have a process which is equivalent to the erosion in a desert. The wind blows and it blows the sand away. In this case, the sand are atmospheric particles. Slowly but surely, the atmospheric gases, which includes water, are carried away and are lost to Mars.
The loss of its magnetic shield could well have meant death for the red planet. Exposed to the wind of radiation from the sun, over millions of years, its atmosphere was gradually blown away, leaving the sterile world we see today.
If we were to turn off the Earth's magnetic field, the same process would occur. The atmosphere of Earth would be exposed to the erosional effects of the solar wind, and it would be slowly carried away.
The fate of Mars suggests that without the protection of its magnetic shield, the Earth could also become a dead planet. Which makes it all the more disturbing to learn that our own magnetic field is fading so rapidly. Evidence of that decline has come from a surprising source. People have been making pottery for thousands of years. Archaeologists study pots to learn about ancient cultures. But these vessels have another story to tell.
Pottery acts just like a magnetic tape recorder. It records the Earth's magnetic field when the pottery is first made.
An ancient pot is a magnetic time capsule. John Shaw has learned how to extract from it a precise measurement of the strength of the magnetic field as it was in antiquity. Like volcanic rock, clay contains tiny pieces of an iron-based mineral called magnetite. At the microscopic level, magnetite contains lots of distinct magnetic regions, in effect, tiny magnets. But in raw clay, these microscopic magnets all point in different directions, so they fail to create an overall magnetic field. That means a lump of clay on the potter's wheel is not itself magnetic. Not yet, anyway.
Now, the interesting part is when the pot's fired.
The intense heat in the kiln erases all the magnetic regions. But as the pot begins to cool, new magnetic regions form in the magnetite. And as the regions reform, they align with the Earth's magnetic field, just like compass needles. With millions of tiny magnets all pointing in the same general direction, the pot itself becomes slightly magnetic. Once it has cooled, the magnetism is locked in.
So if we take an ancient pot like this one, which is from Peru, when it cooled for the first time, it cooled in the Earth's ancient magnetic field, and it became magnetized in that field. And of course, if the field's very strong, then the pot's strongly magnetized, and if the field's very weak, then the pot's weakly magnetized.
By examining pottery from prehistory to modern times, John has discovered just how dramatically the field has changed in the last few centuries.
When we plot the results from the ceramics, this is what we see. Gentle changes as we come forward in time over 12,000 years, a gentle rise, and then a rapid fall as we come towards the present day. The rate of change is higher over the last 300 years than it has been for any time in the past 5,000. It's going from a strong field down to a weak field, and it's doing it very quickly.
In 300 years, the field has fallen 10%, and the rate of decline is increasing. In just a few centuries, it could be gone altogether. So, is the Earth going the way of Mars? There's only one place to look for an answer: the inaccessible region where the field is generated, the Earth's core.
There's a deep, molten heart where these strange attractions start.
But with no way to get to the core, Professor Dan Lathrop is playing with fire as he and his students try to build it in their lab.
Yes, that heater wiring looks pretty good.
They want to find out just what keeps the magnetic field going and what might cause it to disappear.
Trying to test out the new IO Semitronics probe.
They model the liquid metal core with sodium because it's highly conductive and much easier to melt than iron.
Sodium actually at room temperature is really a very soft metal. It's sort of cheesy. Of course, when we heat it up to around the boiling point of water, then it becomes liquid, and that's where we actually run the experiments. But it certainly is a hazard in the lab. If we put sodium down into some water, you get little explosions and burning coming off of it.
What you're looking at here is a sphere which contains about 110 kilograms of sodium. When we run an experiment, we'll start spinning this ball like the Earth is spinning and make measurements of magnetic field that it generates on its own.
What they're trying to create is a self-sustaining electromagnetic dynamo, because that's what they think the Earth is. Scientists have a theory about how the core generates the magnetic field. It's based on the close relationship of magnetism to electricity. In particular, the fact that electric currents create magnetic fields.
Now, there's no electric current going through the coil to start with. The iron filings just go down like pepper in a pan, but if I turn on the electric current, then you can see the iron filings line up with the magnetic field that's produced by the current in this electric coil. So it's really currents inside the Earth's liquid metal core that we think gives rise to the magnetic field.
But what gives rise to the electric currents? The answer to that is where things get complicated. Scientists believe that just as the electric currents produce the magnetic field, so the magnetic field produces the electric currents. The key is that the liquid metal in the core is in constant motion.
If you take a moving conductor, in the presence of a magnetic field, currents get set up inside the conductor.
In the Earth, the moving conductor is 1 billion trillion tons of molten iron, but the effect can be seen in a simple loop of wire connected only to a meter which measures electric currents.
If I move this conductor in the presence of the Earth's magnetic field, then that gives rise to currents. Once you have currents, those give rise to magnetic fields. So it's kind of a curious loop that gets set up in the Earth's core. A little bit of magnetic field couples into the motion of the liquid, gives rise to currents flowing in the core. Those currents cause more magnetic field, which cause more currents, more magnetic field. So it's kind of a feedback loop that can cause the magnetic field to just rise.
If it works in the Earth's core, it should work in the lab. Scientists are not quite sure what got the Earth's dynamo started. It may have been stray magnetic fields from the sun. But to get a small-scale version going, Dan uses a powerful magnet.
We apply a large magnetic field onto the sodium flow inside the sphere, and you can get a feel for how strong the magnetic field is. If we, Dan, turn on the magnets, we can actually see how they attract this chain quite strongly. Wipe out any bad credit cards you might have in a hurry.
If the electromagnetic dynamo theory is right, then the field generated by their miniature core will be stronger than the field they started with, the magnetism rapidly growing by drawing energy from the motion of the liquid sodium conductor. It's something they haven't yet achieved, but already they have revealed a crucial clue to what might cause a planet's magnetic field to fail.
Well, the different experiments that have been run have shown that a moving liquid metal is critical to getting the magnetic field to arise.
So, if the core were ever to cool to the point where the liquid iron solidified and stopped moving, the dynamo would shut down. This may be why Mars lost its magnetic field so early in its history.
Because Mars is a smaller planet, it will have cooled more quickly than the Earth. So there's a very good chance that Mars has simply become too cold to sustain an active dynamo. It could be that the liquid metal core just froze out at some point.
But will what happened to Mars eventually happen to the Earth?
The Earth's core is very slowly cooling at the rate of perhaps 100 degrees per billion years. So eventually, the whole of the core will freeze. At that point, the dynamo will die.
But scientists calculate that the cooling of the Earth's core is so slow that that point lies billions of years in the future.
The Earth's magnetic field has been around for a long time, at least 2 billion years. It has lasted so long because it has a very large energy source in the original heat that the Earth's core inherited when it was formed. And so the Earth can sustain the magnetic field for billions and billions of years of time.
What's more, the history of the field's decline revealed by the pottery record just doesn't fit the idea that the Earth's internal dynamo is shutting down. Surprisingly, the Earth's field is fading too quickly.
If we were to shut down the heat flux in the core, it would take hundreds of thousands of years, perhaps millions of years, for the field to decrease. And that's not what we see. We see a field decrease which is much faster than that, so there is something else going on in the case of the Earth.
But what? Searching for clues to what's happening deep inside our planet, scientists have turned their attention to a chain of volcanic islands in the middle of the Pacific. Here, there's a record of the Earth's magnetic field that stretches back millions of years. A record not of gradual decline, but of a series of spectacular magnetic upheavals.
It's the buzz, what a fool of your sweet magnetic pull. It's the tug that I crave. It's how opposites behave.
On the big island of Hawaii, some of the heat that drives the Earth's dynamo finds its way to the surface.
All right, now I'm in.
For several years now, Mount Kilauea has been continuously erupting.
Well done.
Scientists from the U.S. Geological Survey need to sample the lava to keep an eye on the volcano.
It solidifies pretty fast, as you can see.
But geophysicist Mike Fuller is interested in the lava for another reason: what it tells him about the Earth's magnetic field. It all begins when the lava hits the sea.
You can see the lavas having moved down from the volcano up here, sometimes in tubes, mostly in tubes. Now we're beginning to see it come out and go into the water and form the very newest bit of the island chain of Hawaii. As this lava hits the seawater, of course, it really chills very, very fast. And a very wonderful thing happens. They actually trap in, they record the Earth's magnetic field.
As they solidify and cool, these volcanic rocks are preserving a record of today's magnetic field. But the volcanoes of Hawaii have been erupting on and off for millions of years, building up the islands. Every layer of lava contains a record of the magnetic field at the time of that eruption. So the Hawaiian archipelago is a hidden chronicle of the Earth's magnetism stretching back 5.5 million years. That record shows there have been many fluctuations in the field's strength, but it contains something else of great significance. When lava cools, as with pottery, magnetic regions form within it. Acting like microscopic compass needles, they record not only how strong the field is, but also in what direction it is pointing. Today, the Earth's magnetic field runs from south to north, which is why compass needles point toward the North Pole, and recent lava flows record a field pointing north. But 50 years ago, when scientists measured the magnetism trapped in older lava samples, they made a startling discovery. The microscopic magnets within the lava were all pointing south.
When we go back about 700,000 years, we find an incredible phenomenon. Suddenly, the rocks are magnetized backwards. Instead of them being magnetized to the north, like today's field, they're magnetized to the south.
It seemed that prior to 780,000 years ago, Hawaiian lava must have cooled within a global magnetic field that was running to the south and away from the north, exactly the reverse of today. The bizarre implication was that at some point, the entire global magnetic field had done a sudden 180-degree flip, completely reversing direction.
It was hard for people to accept. They did not like the idea that the field reversed. It took about 50 years to convince people of this. But eventually, that was established, and really by work on this island, because if you keep on going down, you would find that after about another couple of 100,000 years, then it changes again, and you see this sequence going on.
And as they examined samples from older and older lava, scientists found more and more reversals. On average, one every 200,000 years.
And so by the time people had done that, it was pretty obvious that the field did indeed reverse.
But if the field has reversed so often in the past, it must surely do so again in the future.
That the Earth's magnetic field reverses is an extraordinary phenomenon. But this reversal process is quite common. The last reversal was, what, 780,000 years ago. Before that, there was one about 200,000. Before that, again, actually less than 200. So in a sense, we are a bit overdue for a reversal.
So is this why the field is growing weaker today? Could it be getting ready to flip? Scientists needed to discover whether there was a link between changes in the strength of the magnetic field and changes in its direction.
It was a very intriguing problem, something that was screaming out for an answer, and computers were becoming powerful enough to actually solve a full set of equations that describe convection in the core of the Earth and how that motion generates a magnetic field.
In the 1990s, physicist Gary Glatzmeyer decided to embark on a very ambitious experiment. He put all the essential facts that scientists had learned about the Earth's molten core into a computer model, dozens of equations describing its dimensions, temperature, viscosity, and so forth. Then he let the model run to see how the magnetic field would evolve over hundreds of thousands of years of simulated time.
It's important to understand just how long these simulations take. Each time the computer solves the equations, it advances the whole solution one time step. And the time step is typically 10 days. And within 10 days, things don't change much, which means you have to do many, many solutions. You have to solve it millions of times, tens of millions of times, in order to be able to simulate hundreds of thousands of years, which is what we needed. One case may take 6 months of running on the fastest computers in the world. I was using supercomputers from the Department of Energy, from NASA, and the National Science Foundation, and no matter where I was, the first thing I do is make sure the computers didn't crash. So it was something I did every day, 7 days a week, for over 4 years. And I remember there was a period of time, I believe it was in the fall, and I was traveling to other universities and giving talks, and after a number of weeks I came back and decided, well, now I need to look at the details of the magnetic field, and realized that it was in the reverse polarity. It already had reverse. This is something I didn't expect. So then I looked at many snapshots during the time I was gone and realized that the field did indeed reverse spontaneously. This is the first time it happened. We were very anxious to write about it. It was really exciting.
And as the experiment continued, so did the reversals, every 100,000 years or so of simulated time. And crucially, each time the field reversed, the process began the same way.
What's interesting is whenever it has reversed its polarity, its direction, that happened when the magnetic intensity was very weak. So it was decreasing, decreasing. Finally, when it was the dipole part of the field was very weak, then the field reversed.
Here was the evidence that what we are seeing today, a loss of field strength, is indeed linked to the onset of reversals. What's more, Gary could see why reversals are heralded by a weakening field.
Now this movie will show part of a simulation that spans magnetic field reversal. What you see here, blue represents inward directed magnetic field, the gold represents outward directed magnetic field.
In Gary's model, reversals seem to start with the appearance of islands of blue in the gold, and vice versa. These are magnetic anomalies, regions of the core where the field is already flowing the wrong way. As they grow, these patches where the field is reversed start to cancel out the main field, making it weaker and more liable to flip.
You see, as the time goes on, the field becomes more and more complicated, and then you get an anomaly growing in the northern hemisphere where magnetic field now is going out. There's a reversal. Now the magnetic field is outward in the northern hemisphere and inward in the southern hemisphere.
So now the burning question is what's happening in Gary's model reflected in the real Earth? Is the 300-year decline in our field, which the pottery reveals, the work of magnetic anomalies brewing deep in the core beneath our feet? If so, then a reversal really could be in the cards.
If the north isn't true, will I lose my way to you?
Amazingly, there are detailed records that cover exactly this 300-year period. The logbooks of Her Majesty's Navy. For as geophysicist Jeremy Bloxham has discovered, 18th and 19th century sailors were obsessed with the magnetic field.
Back in the days of James Cook, when he was doing his voyages of exploration, a compass was the primary means of navigation. However, a compass needle doesn't point at true north, at the real geographical North Pole. Instead, it points at magnetic north.
For sailors, knowing the difference between true north and magnetic north was a matter of life and death. But as they were well aware, magnetic north keeps moving, wandering about near the pole as the field gradually changes. So navigators needed to measure the difference between magnetic north and true north, the angle of variation. They did this by comparing their compass bearing to an astronomical calculation of true north.
The trick was to find true north, and they could do this by looking at the sun at noon when it's highest in the sky, alternatively by looking at the angle the sun made at sunrise or sunset. Here on the 8th of June 1770 we have a magnetic variation of 4 degrees and 53 minutes east.
Thousands of these observations, together with early measures of the local strength of the field, have enabled Jeremy to reconstruct the ebb and flow of the Earth's magnetism over the past 3 centuries. And it's what this reveals about one region in particular that's significant.
We've seen very abrupt changes in the Earth's magnetic field beneath the South Atlantic Ocean.
Beneath the South Atlantic, Jeremy has found clear evidence for a region of magnetic anomalies, places where the field has already started to reverse. And these anomalies are growing.
As we get into the beginning of the 20th century, we see the emergence of a new patch of reverse flux, a region where the field lines, instead of coming out of the core, are looping back into the core. And that patch then drifts towards the west, hooking up with this other patch of reverse flux to create a large region, what we call the South Atlantic anomaly, where the field is about 30% weaker. And that patch has grown substantially during the last 100 years in particular. So one question we're all asking ourselves at the moment is the Earth's magnetic field about to flip?
In a region of the core 2,000 miles beneath the South Atlantic, the magnetic currents have reversed direction, canceling out the main field, causing its strength to decline. If things continue like this, then we could experience a magnetic phenomenon the Earth has not seen for 780,000 years. A complete flip of the entire global field.
really no question about whether the Earth's magnetic field will reverse again. The question is not if that's going to happen, it's when that's going to happen.
Actually, in the last few hundred years, the intensity of the magnetic field on the Earth has been decreasing, which is an indication that maybe we're in for a reversal. The average time between reversals is on the order of a few 100,000 years. We're actually sort of due for one.
No one has ever experienced a magnetic reversal. If this is really the beginning of a flip, what exactly will happen next? One man who may know is geologist Rob Coe. For 25 years, he's been coming to Steens Mountain in Oregon, a vast heap of hundreds of ancient lava flows.
"16 million years ago, there was a huge series of eruptions here. You can pick out literally hundreds of lava flows over on that wall. Each line delineates a different lava flow. It's over 3,000 feet of overlying flows.
What makes Steens special is that 16 million years ago, when this lava was erupted, the magnetic field was in the middle of a flip. Taking samples from dozens of flows all the way up the mountain, Rob and his colleagues have pieced together a detailed record of this magnetic reversal, although it's so surprising that not everyone accepts it.
What we found as it started to reverse was the strength of the Earth's field decreased dramatically by 80 or 90%.
The field started out pointing south, but as it weakened, the direction of the field began to change erratically. After 300 years, it had swung a full 180 degrees to point north, and the field's strength started to recover.
But it couldn't hold that polarity, and it fell back to reversed, and the intensity crashed again.
Once more, the Earth's magnetic shield practically disappeared, this time for 3,000 years. What was left was changing so fast that Rob found a flow that captured these wild gyrations even as the lava cooled.
And what we found was even harder to believe. The quickly chilled margins in the bottom and the top had one direction, like that of the underlying flow, and the middle portion had a direction that was 60 degrees farther away. It was just as though, while the flow cooled, the field had moved 60 degrees, which if you calculate it out, that comes to about 6 degrees of movement per day. If we were observing this with a compass, you would be able almost to see the motion with your eye. It was truly astonishing and extraordinary.
The lava layers of Steens Mountain suggest we could be in for magnetic chaos, with magnetic north changing from day to day. More seriously, for perhaps thousands of years, the Earth's magnetic shield will be weakened, something that will affect every person on the planet.
The intensity of the magnetic field will be weaker, maybe 10, maybe 100 times weaker than it is today, which means that more cosmic radiation will get through.
This basically opens our defenses so that solar and galactic radiation can hit the atmosphere directly. And this means that the radiation at ground level increases as well.
One estimate is that our overall exposure to cosmic radiation will double, and in some places it could be even worse. Today, the magnetic field focuses space radiation towards the far north and south, where few people live. But as the main field collapses, the weak field that's left will have a more complex structure. Instead of just 2 magnetic poles, there may be 4 or even 8, slowly moving across the Earth's surface.
The structure of the magnetic field won't be the nice, smooth, simple dipole structure that we have today, which tends to deflect charged particles, cosmic radiation, to the poles of the Earth. Instead, there'll be several poles all around the Earth, maybe close to the equator. And so not only will the field be weaker, the field will tend to focus cosmic radiation at low latitudes where most people live.
This unfortunately means more deaths from cancer. It's roughly 15 per million people per year. That is the amount of deaths we're talking about. And if you multiply that over the whole population of the Earth, that becomes a significant number.
It's impossible to know for sure, but the best guess is that every year 100,000 people would die from the increased levels of space radiation. But of course, this would still represent only a relatively small increase in the overall incidence of cancer.
So it's not going to be catastrophic. It'll be something to be concerned about, but it won't be a catastrophic event. And certainly by the time it happens, civilization will have figured out how to deal with it.
The field will come back. In the case of Mars, we know that the field will not come back, and it has been gone for billions of years, so the effect has been very, very serious on the Mars atmosphere. But on the Earth atmosphere, just a few thousand years of no magnetic field are not expected to result in a very large stripping of the atmosphere.
Scientists now know that the magnetic reversal that is inevitably coming will have serious consequences for our descendants, but it won't be a disaster for planet Earth. And as our children's children's children wait for north to become south, they may find that a world without a strong magnetic field has its compensations.
The great thing is that it would be possible to see the aurora just about every night, all over the Earth. So London behind me, for example, we might be able to see great aurora just about every night of the year, shimmering and moving in the sky as the solar wind hits the atmosphere directly and it glows like a neon light.
Aurora will be very exciting. I can imagine a very interesting dynamic magnetic field outside of the Earth during the next reversal.
I would love to see a reversal happen, but it would involve me living rather longer than I planned to, but that would be very nice. In fact, it's one of the great tragedies of life. We never see how these things work out.
I'd really like to know how it does it and why it does it, and when will it do it again?
None of us will be around for the next magnetic reversal, but on NOVA's website, get a sneak preview of what the night sky will look like when it happens. Find it on pbs.org. To order this show or any other NOVA program for $19.95 plus shipping and handling, call WGBH Boston Video at 1-800-255-9424. NOVA is a production of WGBH Boston. Major funding for NOVA is provided by the Park Foundation, dedicated to education and quality television.
Science. It's given us the framework to help make wireless communications clear. Sprint is proud to support NOVA.
We see an explorer. At Microsoft, your potential inspires us to create software that helps you reach it. Your potential, our passion.
And by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you.
I am PBS.